Today in this lesson, we're going to talk about the concept of functions. We're going to discuss basically define functions. Then we'll look at some example of typical functions used in computer science and software. And then we'll look at some properties of functions such as one-to-one functions, on-to functions, inverse functions, that kind of thing. Okay. So our first definition will be, what is a function? A function from x to y is a subset of a Cartesian product, x cross y, having the property that each x in x, there is exactly one y in y, where xy is an element of the function. We sometimes denote a function f from x to y with this notation, f colon x arrow y. It just means the function takes elements of x into the elements of y. The set x is called the domain of f, and the set y is called the codomain of f. Okay. So the range, what we call the range of a function, is a set of all elements y that are in the xy coordinates of f. So the codomain and the range have a slightly subtle difference. The codomain is basically the set receiving the data, but the range is the actual values from the codomain that the function sends things to. So it's possible there's more in the codomain than there is in the range. Let's look at this example. Let's say you have a set f, which is 1a, 2b, 3a. And this is a function from x equals 1, 2, the set 1, 2, 3, to y, the set a, b, c. Each element in x is assigned a unique element in y. See, 1 only goes to a and nothing else. Okay. So 1 is assigned a unique value of 2, of A. 2 is assigned a unique value B, and 3a. It's okay if 1 and 3 both go to A, but it's not okay if 1 went to A and 1 went to B in the same function. You can't have that. Wouldn't be a function then. We can often picture this stuff with what's called arrow diagrams, like this. So here is the set X. It has 3 elements, 1, 2, 3. And then the set Y has 3 elements, A, B, C. And then the arrow just means 1 goes to A. So that would be 1A. 2 goes to B. You get 2B. And 3 goes to A. Okay. So notice in this picture, the codomain is Y. The range is just AB. So that's what I was saying. It's possible the codomain will have elements in it that are not in the range. The range is AB because all elements X only go to A and B. So this distinction between codomain and range we make here in other courses you might have had, calculus, stuff like that. They don't usually draw that distinction. They just talk about the range of a function. Okay. Here's a case where X, the domain is 1, 2, 3, and 4, and Y is A, B, C. And then here are the Cartesian products that you have. X is not a function because X is not assigned to an element Y. There is an X, namely 4, that's not assigned to Y. So to be a function, and if you go back and look at the definition of a function, it says that for each X and X. So if you have, as in this case over here, you have X as a domain, 1, 2, 3, 4, and Y as a codomain ABC. This can't be a function, or this set of ordered pairs up here can't be a function because number 4 is not included in this one. In other words, you have to represent whatever you ordered pairs you put in here. Every element of X has to be represented as a first coordinate in an ordered pair. Okay. So here's the arrow diagram for that. Mhm. Okay. The set 1a, 2b, 3c, and 1b is not a function from x equals 1, 2, 3 to y equals a, b, c, because 1 is not assigned a unique value in y. 1 is assigned a and at the same time also assigned b. Okay. This is the discrete function analog to violating the vertical line test for continuous functions that you see in algebra and calculus and such. Since the one x coordinate has two y coordinates, that's like a vertical line test kind of thing. In an arrow diagram, this is, you can't have two arrows coming off of a point in the x set going to different points in the y set if you want to be a function. So this is what it looks like when you're not a function. Okay. Suppose we define a function by the rule fx equals x squared. Okay. So for example, f2 equals 4 and f minus 3.5 equals 12.25 and f0 equals 0. We often find functions defined this way, but the definition is incomplete since the domain and codomain are not specified. If we are told the domain is a set of all real numbers and the codomain is a set of all non-negative real numbers, in ordered pair notation, we would write f equals x comma x squared, where x is a real number. The range of f is a set of all non-negative real numbers. So here's the graph. So the domain would be all real numbers, right? And the range of a graph of x squared, the smallest it ever is 0, otherwise it's positive. So the range is 0 to infinity on the y-axis, whereas the domain is minus infinity to infinity. Okay. Here's a graph of a function, or that function 1, 1, 1, 3, 2, 2, 0, 0, 3, 0. So this is not a function because you have two coordinates with an x value is 1. Remember I said that's the analog of the vertical line test in real number functions, in continuous functions. If I draw a vertical line through 1, I hit another point, 1, 3. So you can't have two points with the x value of 1 and be a function. So this is perfectly consistent with other definitions of functions you might have seen in earlier classes. Okay. So some of the special functions that we find useful in programming and computer science in general, one of them is the modulus operator. So as a definition, if x is an integer and y is a positive integer, we define x mod y to be the remainder when x is divided by y. Okay. So 6 mod 2 is 0 because 2 divides into 6 3 times and there's no remainder. So if 2 divides into a number, if you have x mod y and y divides evenly into x, then the answer is 0. 1 mod 5 is also 0. Same argument. Because if you divide 1 into 5, I get 5, I get no remainder. 12 mod 8. If I divide 12 into 8, I have 0. 0 times 12 is 0. 8 minus 0 is 8. So the remainder is 8. So basically, if you have a mod number, say like 12, any number that's less than 12, 0, 8, 12, 8 mod 12, 9 mod 12, anything that's less than this mod number, the answer is just that number. So if I had 9 mod 12 here, it'd be 9. If I had 11 mod 12, it would be 11. If I had 13 mod 12, it'd be 1. Okay. 199,673 mod 2 turns out to be 1. If I divide 2 into any number, there's only two possible remainders, 0 or 1. Okay. So all this is telling me is that 199,673 is an odd number because 2 divided in this doesn't go evenly. It leaves a remainder of 1. If you've taken any programming classes in Java or something like that, you'll recognize this percent symbol. That's what they use in a lot of programming languages to do the modulus calculations. If I was to write a piece of code and I said x equals, like int x equals 199,673% 2, the answer would be 1. So a lot of times in code, that's how we determine if a number is even or odd, right? We just say, oh, well, take the number percent 2. If I get 0, it's even. If I get 1, it's odd. Here's another question. What day of the week will it be 365 days from Wednesday? Okay. The solution's pretty easy. 7 days after Wednesday, it'll be Wednesday again. 14 days after Wednesday, it'll be Wednesday again. In other words, whatever day you're at, add 7 days, it's the same day as far as the name of the day goes. And in general, if n is a positive integer, 7n days after Wednesday, it's Wednesday again. So thus, all we need to do is subtract as many 7s as possible from 365 to see how many days are left, which is the same as computing 365 mod 7. Since 365 mod 7 is 1, 365 days from Wednesday, it will be 1 day later, namely Thursday. So you might have noticed that in the calendar. For years other than leap year, when an extra day is added to February, the identical month and date in consecutive years moved forward 1 day. Okay. Another important type of function that's used in software is called a hash function. Okay. Suppose that we have cells in computer memory indexed 0 to 10. So say an array of 11 elements indexed 0 to 10. We wish to store and retrieve arbitrary non-negative integers in these cells. One approach is to use what's called a hash function. A hash function takes a data item to be stored or retrieved and computes the first choice for a location of that item. So in this problem here, we're going to store or retrieve the number n. We might take as a first choice for the location n mod 11. Mod 11 because there's only 11 cells, okay, 0 to 10. Our hash function hn equals n mod 11. So basically, whatever number I want to store, for example, if I want to store 15, I'll say h of 15, which is 15 mod 11. 15 mod 11 is 4 because 4 divides into 15 once. 1 times 15 is, so 1 times 11 is 11. 15 minus 11 is 4. So that's a remainder of 4. So what it means is I'm going to store the number 15 at the position 4 because 15 mod 11 is 4. 558 mod 11 turns out to have a remainder of 8. So it goes here. 32 mod 11 is 10, right? Because 11 will go into 32 twice. 2 times 11 is 22. 32 minus 11 I'm sorry, 32 minus 22 is 10. So 32 gives 10 here. Now, if I go back to search, later on I say, find me the index where 132 is stored. You just go H132 and mod 11. You're going to end up getting the number 0 because 11 divides evenly into 132. So 132 is stored at index 0, or at least that's your first look. Okay. So you already put it in there earlier, and then to retrieve it, you just use the same function, get the index, go straight to that index. Okay. So hashing functions can be, a very useful way of quickly storing and retrieving data. And particularly if the data is like an object or a database record or something like that, it makes it pretty easy to do it. That's where the name hashtag comes from like Twitter or what X, whatever it's called now. Hashtag just means when they enter that hashtag, it goes to a certain part, pulls certain records from their database to display for you. So the hashtag becomes like a key to the database. Now suppose we want to store 257. So we calculate H257 and we get 4. So, oh, good, we're going to stick it in 4. We go to 4 and go, oh, darn. 15 is already stored there because it is possible for more than one number when you apply a mod to it to give the same answer. Okay. So in this hash function scenario, when the answer is the same, 4, we say a collision has occurred. A collision. Okay. So what do you do when a collision is? You're going to write 257 into index 4 if it's already got a number. What do? Well, you have to come up with a collision resolution policy. Is required to follow. Okay. If we use collision resolution policy, we store 257 at locus 6. So with 0 assumed to be followed through 10. So our simple collision resolution is just find the next highest empty cell. Okay. So what happened when he did 257, he got 4, he went here and he went, darn, it's already occupied. What's my collision resolution policy? Just move down the array till I find an empty spot, which turned out to be 6 at that point, and throw the number in. Okay. When you go to retrieve, say I want to retrieve the index that's holding 257. So I put 257 in there and I get 4. So I can't just say it's at 4. I have to go look at 4. What's in there? It's not 257. Then I just say, okay, if it's not at 4, is it 5? No. Is it at 6? Yes, there it is. And it returns 6. The interesting thing about node collisions is notice he did n mod 11. And you could argue maybe should have done n mod a bigger number. And maybe you're less likely to get collisions. That is true. Obviously, the bigger the mod number, the more elements you're going to have. It turns out, or some mathematicians have shown, that a function like n mod 11 is, as long as that mod number, in this case 11, is a prime number, that will minimize your probability of collisions. I mean, you could mod any number, you could mod 12, but probably you're going to have more collisions with numbers in a modded 12 array versus a modded 11 array or a modded 13 array. So if you use a hash function like this, you want to make sure your mod number is a prime number. Supposedly that will minimize the chances with the number of times that you'll have a collision like this case where 257 is supposed to go into index 4, but it can't because 15 is there, so it had to go into 6. Another important type of function that's used a lot in computer programming is pseudo-random numbers. The pseudo-random number is not truly random, but it's pretty close. Hence, that's why they call it pseudo. It's used in all kinds of modeling programs that involve weather, finance, video games, which is just a type of model. Use pseudo-random numbers because those random numbers might generate, random conditions in the game that you have to deal with. Okay. There's a lot of ways to generate pseudo-random numbers, and you might remember from Java programming or Python or something like that, they give you a function to generate a pseudo-random number. So you don't have to actually write it yourself. But we're going to look at how to do one case. Okay. The method usually used to generate pseudo-random numbers is called linear congruential method. Congruential method. This method requires 4 integers, a modulus m, like 11 was earlier, mod 11, mod 10. You need a value for that. A multiplier a, okay, the increment c, and then a seed s. The seed is like your starting point. You also have rules. A has to be greater than or equal to 2, and it has to be less than whatever your modulus is. C has to be greater than or equal to 0 and less than your modulus. And the seed just has to be greater than or equal to 0, less than your modulus. Okay. We set the first element in the random number list, x0, to the seed. That's why they call it the seed, because all the rest of the numbers grow from it. The sequence and pseudo-random number generated numbers are generated x1, x2 on up is given by this formula. Xn equals AXN minus 1 plus C mod M. The formula basically computes the next pseudo-random numbers. You start with one you already know. So if x0 is s, then you can start with x1, because if n is 1, n minus 1 is 0. Okay. So here's what he does. Remember, m is 11. We take m to be 11, a to be 7. So our modulus is 11. Our multiplier is 7. Our increment is 5, and our seed is 3. So x1, whatever this n is here, this is the next one down. So x1 is going to be ax0 plus c mod m, okay, which is equal to 7, because that's our a. x0 was 1. Oh, x0 was 3, so 7 times 3, right? ax0 plus 5. So it's at 26 mod 11 will be 4. So my next random number was 4. Okay. x2, since n is 2, n minus 1 is 1, so x2 will equal ax1 plus c mod m. Well, a is 7. x1 I just computed to be 4, so that goes there, plus 5. So now I got 28 plus 5 is 33. 11 divides evenly into 33. So my random number x2 is 0. So I got the seed, which was 3. That would be x0. x1 is 4. x2 is 0. If I repeat this calculation, I get x3 is 5. x4 is 7. x5 is 10. x6 is 9. x7 equals 2. Okay. x8 is 8. x9 is 6. x10 is 3. Notice 3 on the 10th one, I got 3, which is the same as my seed was. So if I keep going, it's just going to replicate. The next one will be 4. The one after that will be 0, 5, 7, 8, back up to 10. Okay. So you no point going any further, which is value C. Thus the sequence repeats 3, 4, 0, 5, 7, etc. Okay. But you've got that many. You've got 10, or you've got essentially 9 random numbers there, or 10 random numbers generated. Okay. That you can use for things. So that's how you generate, or a function for generating what's called pseudo-random numbers. And usually when they do that, they use really large seeds and a really large m to get just tons of different random numbers. Yeah. It used to be in textbooks, like statistics textbooks and all, they'd have tables of random numbers, and they were generated probably with this algorithm. Okay. Another important function in computer science, math, and so forth is called the floor of a number. Okay. The floor of a number, so the number that goes into the function is going to be a real number with decimals. The number that comes out is an integer. Okay. And so if we the floor of x, it's called denoted. It looks like the absolute value function, but it has these little hooks at the bottom. So it's denoted that is the greatest integer less than or equal to whatever you put in there. So sometimes the floor is also referred to as the greatest integer function. The ceiling of x, denoted this, again, looks like absolute value sign, but notice it has little hooks up there, is the least integer greater than or equal to x. So sometimes this is also called the least integer function. All right. So as an example, the floor of 8.3 is going to be 8, because 8 is the largest integer less than or equal to 8.3. The ceiling of 9.1 will be 10, because 10 is the smallest integer greater than equal to 9.1. The floor of negative 8.7 is negative 9. Okay. Because then the largest integer smaller than minus 8.7 is minus 9. Because remember, minus 9 is smaller than minus 8.7. The ceiling of minus 11.3 will be minus 11. Because again, the smallest integer bigger than negative 11.3 is going to be a negative 11. If it's already a whole integer, then the ceiling or floor of the integer is just the integer. So ceiling of 6 is 6. The ceiling of minus 8 is minus 8. Okay. So the floor and the floor and mod function are both used a lot in calculating things like dates and times and types of hash functions and all kinds of stuff. There's things you can use this for. Here's the graph of the floor. So if you're at 0, the floor of 0 is 0. So that's why that's square brackets. Any number up to 1, but not including 1, say like 0.5, the floor of 0.5 would be 0. The floor of 0.9 would be 0. The floor of 0.9999 would be 0, and so forth. Once you hit 1, the floor of 1 is 1, so it jumps up here. So now you have square brackets here. And everything from 1 up to 2, not including 2, like 1.5, 1.25, 1.3789, 1 point whatever, its floor is 1. Once it hits 2, it jumps up to 2. And likewise back here, if I take anything less than 0 but greater than or equal to negative 1, the floor is negative 1. Take, for example, minus, I don't know, minus 0.01. The floor of minus 0.01, again, will be the largest integer less than or equal to minus 0.01, which would be minus 1. So since 0 is included here, it's open bracket here all the way to negative 1, and that just extends the graph. Graphs like this are often called step functions because they kind of looks like a cross section of a staircase. Here's the ceiling. The ceiling, notice everything in the ceiling is shifted 1 unit left, and the right-hand side are square brackets and the left-hand sides are open brackets. So like between 0 and 1, pick a number of 0.6. The ceiling of 0.6 is 1. And that holds true all the way up to 1. The ceiling of 0.0001 is still 1. But once you hit 0, it drops down to 0. Okay. So that's the graphs of those two functions. Okay. So here's an example where we might use it. Suppose you have a first-class postage rate for mail up to 13 ounces. And that first-class rate is 92 cents. So your first-class postage rate for mail up to 13 ounces is 92 cents. But that's only for the first ounce, or a fraction of half ounce, quarter ounce. Okay. Then there's 20 cents additional for each ounce after that first ounce. or fraction thereof. So 1.2 ounces would be 92 plus 20 cents. So the postage function, PW, is a function of the weight of the letter or package or whatever. So PW will be 92. That takes care of anything below 1 ounce or uh, below 13 ounces. And then there's additional 20 cents for every ounce after that. So you take 20. First there's 13 ounces, 92 cents for the first ounce. Oh, first ounce. Okay. So the first ounce, not first 13 ounces. Good. So here you have up to 13 ounces. This is 92 cents for the first ounce plus additional. So you have 92 cents plus 20 cents for each additional ounce. But you don't want the 20 cents. You don't want to multiply that for ounce number 1. So you have to say weight minus 1. So if I only buy 1 ounce, P of 1 will be 92 plus 20 times the ceiling of 1 minus 1. 1 minus 1 is 0. 20 times 0 is 0. So you just get 92 for 1 ounce. Anything bigger than 0 and less than or equal to 13, you use this formula. So if I do 2 ounces, it would be 92 plus 20 times 2 minus 1, which would be 1. So it'd be 92 plus 20, which would be 112. Okay. So notice the statement says the 92 cents for the first ounce or fraction thereof, and 20 cents for each additional ounce or fraction thereof. So for each additional ounce, you get the W minus 1. The fraction whereof is taken care of by the ceiling. So for example, down here, what is the postage of 3.7 ounces? It's 92 for the first ounce. It's 20 times the ceiling of 32 minus 1. I'm sorry, 3 minus 1, which is 2.7. So it's 92 plus 20 times the ceiling of 2.7. Okay. Well, the ceiling of 2.7 is 3, so that's how we take care of any part thereof or any fractional ounce is with the ceiling. So you get 92 times 3 plus 20 times 3, which is 152 cents or $1.52 if you want to look at it that way. P2, same thing, 92 plus 20, ceiling 2 minus 1, 92 plus 20 times ceiling 1. Ceiling 1 is just 1, so it's 90 plus 20 or $1.12. So that's a place where you can use. So this is easy to program this into a computer because computers have, like for example, in Java, in the math library, you have math.ceiling. And you just plug in a number and it gives you the answer. Here's the graph of the postage weight thing. So if you're 1 ounce or less, you're 92 cents. If you're 0 ounces, you're 0. That's why it's open bracket. Once you go above 1, like 2, anything from 1 to 2 ounces is 112, anything from 2 to 3, and so forth. Okay. So there's a use for the ceiling and or floor function. An important theorem is in division and number theory is called the quotient remainder theorem. And this states that if d and n are integers and d is greater than 0, there exists an integer q called the quotient and r called the remainder satisfying this formula. And the original number and is equal to a number times the quotient plus the remainder. So if I go through and I divide everything by d, I get n over d. I would get dq over d, which would end up being q. I get r over d. Since r over d is always going to be greater than or equal less than 1, I can take the floor of n over d equals the floor of q plus r over d. The floor of q plus r over d is generally going to be q. Okay. So this way we may compute the quotient q as n over d. Having computed q, we may compute the remainder r equals n minus dq. Okay. So this is just an example of the quotient remainder theorem where it's using the floor um, to describe how it works. Example here. Suppose we divide 36844 by 2427. It comes out to like 15.18088. I don't know, probably infinite expansion. Thus, the quotient Q is going to be the floor of this division. Well, since the result of the division is 15.1808888, the floor would just chop off that decimal part and be 15. So the floor technically does what they call truncate a number. If you take any number with a decimal expansion, truncate it, just chops off the decimal part. And this leaves you with a whole integer. So, but and that's what this Q, the floor of 36844 divided by 2427, you get this 15-point stuff, but the floor chops everything from the decimal on out. So you're just left with 15. But that's cool. Once you can figure out the remainder from that by going taking 36844 mod 247, and then R is equal to 36844 minus 2427 times 15. So he just divides the 15 into the number. Okay. I'm sorry, not the 15. He divides the 2427 into the number, and he'll get an answer and a remainder. Okay. So he just chops off the remainder, takes the floor of it, multiplies it by the number he divided into, and then subtracts it from the original number, and what's left over is your remainder. So in other words, he did this. Oops, sorry. He did this division right here, 36844 divided by 2427. He got 15 point something or other. But by taking the floor of it, you just get the 15. So then he takes the 15 and he multiplies it by the 2427, which will give a number smaller than 36844 because he got rid of the decimal part. So if he takes the original number, 36844, subtracts from it what he divided into it, the 2427 times 15, which is the result of taking the floor of the division of the two things. That'll give you a number a little bit smaller than 36844, or at worst case, the same as 36844. And that difference is your remainder. So the n dq plus r becomes 36844 is equal to 2427 times 15 plus 439. Okay. Right. Here's another definition for functions. It's called a one-to-one function. So function f from x to y is said to be one-to-one, also known as injective, if for all x, x1, and x2 in your set x, if fx1 equals fx2, then x1 has to equal x2. If that's the case, you have what's called a one-to-one function. Okay. Okay. So here's an example. Here's a function that takes x, 1, 2, 3 into y, a, b, c, d. So here's a function 1b, 3a, 2c. This function is one-to-one because every second coordinate only comes from one first coordinate. Right. This one, 1a, 2b, 3a, is not one-to-one because the y-coordinate a comes from two different x-coordinates. And the function says if the y-coordinates are equal, then the x's have to be equal if it's going to be one-to-one. But here I got y-coordinate a and a here, but their x's aren't equal. One is 1, one is 3. So this is a case of one that's not 1 to 1. Here's an arrow diagram. The one on the left, f is 1 to 1 because every coordinate in the y file that's coming from some x comes from some x file. Okay. Over here, it's not 1 to 1 because 3 and 1 are both going to the same value in y. So in sort of real number graph terms, let's see what I can do here. In real number graph terms, you're going to see, alrighty, I am sharing this, right? Yep. Okay. So remember the graph x squared? It's terrible, but you get the idea. Remember the graph x squared, you were a function because you could draw vertical lines and you only hit the graph of the curve one time. Right? But if I draw horizontal lines, I would hit the graph more than once. So if I look at a graph of x cubed, it looks something like this. It's still a function. Vertical lines only hit it once, but it's also 1 to 1 because horizontal lines only hit at any given value, y equals something. It only hits the graph once. So y equals x cubed is a 1 to 1 function. It's a function and 1 to 1. Y equals x squared is a function, but it's not 1 to 1. Another way you can show y is not 1 to 1, or show y equals x squared is not 1 to 1. All you have to do is find a counterexample. Because remember, to be 1 to 1, if f of x1 and f of x2 are equal, then x1 and x2 has to be equal. But if I take x equals 1, then f of 1 is 1 squared, or 1. If I take x equals -1, f of -1 is -1 squared, which is also 1. So what that means is I've got two f's. I got f of 1 and f of -1 that are both 1, but x1 is 1 and x2 is -1. They're different. So that's my counterexample. It can't be 1 to 1. Okay. All right. All right. Okay. All right. Prove that the function 2n equals 2n plus 1 from the set of all positive integers to the set of all positive integers is 1 to 1. Okay. So remember, to prove this, we must show for all positive integers n1 and n2, if fn1 equals fn2, then n1 equals n2. Okay. So what you do is you say, okay, well, fn1 is going to be 2 times n1 plus 1. Okay. fn2 will be 2 times n2 plus 1. Okay. If f is 1 to 1, then I should be able to equate these two. If these two are the same, what happens? So I have 2n plus 1 equals 2n2 plus 1. So I have 2n1 plus 1 equals 2n2 plus 1, just setting these equal. Right away, I could subtract 1 from both sides, and I'd end up with equivalent expression, 2n1 equals 2n2. Then I can divide both sides by 2. And when I do, I get n1 equals n2. All right, so what did I just show? That f of n1 equals f of n2 can only happen if I set them equal, right here, then the only way that that can be equal is if n1 equals n2. That's what this algebra shows. Okay. So that's how I prove that the linear function 2n plus 1 is 1-to-1 on the set of positive integers. Here's another one. Prove that the function f of n is 2 to the n minus n squared from a set of positive integers to a set of positive integers is not 1-to-1. That's pretty easy. So we must find positive integers n1 and n2 such that n1 does not equal n2 and such that f of n1 equals f of n2. Okay. So in other words, we're looking for a counterexample. Two integers that are different, but if I plug them in here, I get the same value. If I can do that, then I know it's not 1-to-1. So the first thing I'll do is I'll take n1 to be 2. So what's f of n1? Well, it's f of 2. So what's f of 2 mean? It means whatever I plug in for n here, I plug in for n in the formula up here. So that's 2 to the 2 minus 2 to the 2, which is 4 minus 4, which is 0. Okay, so far so good. Now we'll take n2 to be 4. Okay, f of n2 would be f of 4, which would be 2 to the 4 minus 4 squared, because I'm plugging in n equal 4. So 2 to the 4 minus 4 squared. Well, 2 to the 4 is 16. 4 squared is 16. I subtract them, I get 0. So what do you know? I've got an f of n1 and an f of n2 give the same answer, namely 0. But n1 and n2 are different. N1 is 2, n2 is 4. Okay. Therefore, the function can't be 1-to-1. And I proved it's not 1-to-1 with this example. Okay. Another property of functions we have is a function f from x to y is said to be onto y, or surjective, if for every y and y there exists an x and x such that fx equals y. In other words, every y comes from some x. So every y in your y file, every point in there is a result of some x in your x file having the function applied to it and go into that y. Okay. So to be onto, you got to hit everything in the codomain, essentially. Okay. So we're going to prove that the function f of x equals 1 over x squared from the set x of non-zero real numbers to the set y of positive real numbers is onto y. So the key thing is when you have questions about 1-to-1 and onto, you have to state what your domain is and your range or codomain is. So he's saying this function takes a set x of non-zero real numbers. So that's like 1, 2, 3, half, 3 halves, 4, pi, whatever, to the set of positive real numbers. Okay. So non-zero real numbers means you can have negative numbers too, because when you square them, they become positive. Okay. All right, so we must show that for every y and y, there exists an x and x such that fx is y. So what we're going to do is substitute in this formula instead of f of x, we're going to, where there's an f of x, we're going to put y. So 1 over x squared equals y. Then what we're going to do is solve for x, which means we're going to multiply both sides by x squared, divide then both sides by y, and take the square root. When you do that, x becomes plus or minus 1 over root y. Okay. binary this substance. I forget what the domain was. Let's see. It said, okay, the set of y positive real numbers. All right. Since we're talking about positive real numbers that the set y has, I don't need the minus case, so I can just look at the plus case. Okay. So x equals 1 over root y. Then for each x and x, and we could just as well have taken x equals minus 1 over root y. Either one would work, but we went with the positive. So for each x and x, for every y and y, there exists an x, namely 1 over root y. Okay. So that's what this is telling us. For every x and x, and thus for every y and y, there exists an x, namely 1 over root y, such that f of x, f of 1 over root y, equals 1 over root y squared, which is y. So every f of x equals a y. So every element in y is hit. Okay. Therefore, f is onto. Okay. Here I'm going to say prove that the function f of n equals 2n minus 1 from the set x of positive integers to the set y of positive integers is not onto y. So not onto means there's going to be stuff in the y function that never came from anything in x or anything in f. So I can put in some elements for x and it won't go to, there'll be elements of y that will never be gotten by this function. So first of all, we find an element m and y such that for all n and x, fn is not equal to m. Okay, can I find one of those? And the answer is yeah, because f of n is an odd integer. No matter what n I plug in, I'm going to get an odd number from this formula. Okay, which means, see, y was all positive integers. So positive integers are either made up of odd integers or even integers and both. So the set of all positive integers is every odd and even integer. But my function only goes to odd integer. No matter what I plug in for n, even or odd, the result is an odd integer. So that means every integer in y is not being gotten to by the function. So there's a whole bunch of things in the codomain that didn't get hit. Therefore, it can't be 1-to-1. Okay. If you have a function that turns out to be both 1-to-1 and onto at the same time, they have a name for that. They call it a bijection. Suppose f is 1-to-1 onto function from x to y. It can be shown that the set of all y-x's, such as xy is in the function, is 1-to-1 and onto function from y to x. And this is defined as the inverse function. So in other words, as long as your function is 1-to-1 and onto, then every xy is in your function. You can show that if I reverse the x and y to x, I also get a 1-to-1 onto function. And that function is called the inverse. And notice the inverse is just a set of all ordered pairs. The inverse function is a set of all ordered pairs where the original order pairs came from your function and you just reverse the order. Okay. That's what an inverse function is. So for example, the function 1a, 2c, 3b. Its inverse would be take these ordered pairs and reverse them. Becomes A1, C2, B3. Okay. Now you might recall an exponential function called 2 to the x. 2 to the x is a 1-to-1 function from the set R of all real numbers onto set R plus. Okay. It's also onto R plus. Of all positive real numbers, derive a formula for f inverse y. Okay. Suppose that yx is f inverse, that is, f inverse of y is x. Thus, xy is in the function, and thus y equals 2 to the x. By definition, the inverse function of 2 to the x is log base 2y of x. Or you could also say LGY equals x. combine the fact that f inverse y equals x equals log 2y. That is, for each y in R plus, f inverse y is the logarithm base 2 of y. Okay. All right. Thus, if I summarize the situation saying that an inverse of an exponential function is the logarithm of the function. So in other words, the inverse functions for logs are exponentials. So the inverse of log 2y is 2 to the x. The inverse of 2 to the x is log 2y. The inverse of e to the x is ln y or ln x. The inverse of 10 to the x is log x. Without, if you don't specify base with the log, it's automatically base 10. So that's the inverse function of 10 to the x. Okay. If I let g be a function from x to y and let f be a function from y to z, I can create what's called a composition of f and g, denoted f circle g, or f circle g of x is equal to f of g of x. And this combined function goes from x to z. Pictorially, it kind of works like this. Suppose you have a function x, you have x, and g takes x to y, say. Okay. So g takes one from elements from x to elements of y, and f takes elements of y to elements of z. Okay. Elements of y from elements to z. So in other words, say I plug in 1 goes to a, right, under g, and under f, a goes to y. Okay. That's called, so I could write a function, essentially what's called the composition of the two functions, and say 1 comes from the x file and y comes from the z file, right? So f composed of g would be 1 to y, 2 to y, 3 to z. So you can write it in arrow diagram for the set x is 1, 2, 3, the set y is a, b, c, the set z is x, y, z. So if I do it the long way, first thing I do is I take number 2, say, apply it to g. G says send 2 to y's point A. So follow the 2 arrow to A. Then I take the letter A and I apply it to F. And A goes to Y. So this says this goes to Y. So therefore, the composition of F and G of this for 2 is 2 all the way to Y, or right this way, F circle G, 2 to Y. 1 the same way, 1 goes to A goes to Y. So therefore, in the composition function, 1 goes to y as well. Okay. So suppose you have, if f of x is log 3 of x and g of x is x to the 4, then f of g of x is log 3 of x to the 4. And g of f of x is log 3x to the 4th power. So just realize f of x is log 3x, g of x is x to the 4. If I say f of g of x, what I'm saying is everywhere you see an x in this formula, you put g of x. Well, g of x is x to the 4th. So if I take f of 4, x to the 4 rather, I'm going to this formula, and everywhere I see an x, I'm going to put x to the 4th. So that's where log 3x to the 4th came from. Go the other way around, g of f of x. F of x is log 3x. G of x is x to the 4th. So if I plug in log 3x for x, I'm going to have log 3x to the 4th power, which is what I have here. That's called composition of functions. Here's another example. Suppose a store offers 15% off the price of certain items. A coupon is also available that offers $20 off of the price of the same items. The store will honor both discounts. So the function dp is 80.85p. That's the function. If I just plug in the price, I'm paying 85% of the price because of the 15% off sale. So that gives a cost with 15% off. The function CP is P minus 20 is just the price minus whatever the $20. There's no percentage, it's just $20. Okay. Using the cost of using $20 coupon, that's what that is. Okay. So D circle P is going to be D of C of P. So D, remember the function D was 0.85p. The function of C of P is P minus 20. So we're going to take P minus 20, plug it in for the P and D of P. So that's where the 0.85 times P minus 20 comes from. Then I multiply 0.85 times P minus 0.85 20 is 17. There's the function that I can plug in a price and get what I have to pay with both discounts. Okay. So that's an example of using composition of functions. Okay. Another definition, a function from x cross x to x is called a binary operator on x. Okay. Example, let's let x be 1, 2, 3 on up to infinity. And we define f of xy to be x plus y. Okay. Where xy is an element x, f is a binary operator on x. So in other words, I'm taking an ordered pair, xy, I'm plugging it into a function to get one number out. And it's called a binary operator. A function from x to x is called a unary operator. Okay. Let U be the universal set, say. And we define a function that f of a set is its complement, where the elements of x are the power set of whatever my universal set is. So in other words, all subsets of x, of U rather, make up the domain of the function. Okay. So plug in any subset of x, the resultant function is x bar, which is, remember, the complement. And remember that x bar union x and gives you the whole U, right? But it's a binary, it's a unary function. It's one in, one out. Another example of a binary number on logic operators, for example, if x is a set of propositions, then the negation is a unary operation, just negating x. Okay, just negating whatever proposition x represents. So if x is true, negating it's false. That's a unary operation. Okay. Okay. So that is the lesson for functions, or the general definitions of functions.